Today, we want to keep talking about parameterized curves. Here's where we describe a position in space using 2 or the 3 coordinates, not in relation to each other, but as functions of some parameter. So we have a parameterized curve. It could be, there's some x of t, y of t, and sometimes even a z of t. So we've been describing points in space, x, y, and z. What I want to start doing is describing these points as position vectors. So we have a point in space, x, y, and z. I just want to imagine it as a position vector. So here's the point x, y, z. And I want to imagine it as a position vector we introduced this idea last time because I wanted to, when we were talking about parameterizing a line, where our direction was described with a vector, and then to make sure we can add the vector times t to some starting location, we described that location with a point, or that location with a vector, and no one questioned it, so I think we're okay. So what we had done previously is describe a direction vector. Can't remember what color I used, but it's not important. Here's the direction describing the line. And we need to describe where this started. And so P naught was our initial starting position. We're using the starting position as a vector. So we were expressing our starting position as a vector. So it's not that unusual to describe locations with vectors. But when we're describing a position vector, one end is the origin, and then the other end is the position. And then V was the direction. And then this gave us an entire line in the direction of V containing the point P. So describing positions as a vector, not that. Also, if we think about P naught as a position vector, we just put one end at 0 and the end at P naught. If we do P naught plus 1 times V, that would put us at this location. And we could just use that same position to describe this vector to describe that position. So we're all good here. Position can be a vector. So we've described P of t, we can describe a position vector. And since we have talked about direction in the past, we talked about these curves and their direction as they move through space, we might want to talk about the velocity. or which direction they're going. So velocity, we know is the derivative of the position. It's how position is changing with respect to t. The good news is to find, if we have a position vector, to figure out it's made up of three functions, our parametric equations of our curve. To write the velocity vector at any point, we just need to take the derivative of the three components. That is, given a position vector, the velocity vector is exactly what you think it would be. Moreover, the exactly how you think it would be stuff continues. If I've got a curve running around through space, it could be doing all kinds of crazy stuff that we normally can't do with functions. If I pick a point, say t naught, and calculate the velocity vector at that point, what am I going to be drawing? So v of t is just going to be p prime of t. Just take the derivative of each of the three coordinates. So if I pick a point, let's say t naught, so this location is p of t naught. That's not a good location. That's a little bit better. How would I draw the velocity vector at that point? What am I going to draw? What do derivatives tell us about? Since I'm looking at a curve and describing its position, and then taking the derivative of that curve to describe its velocity, the velocity vector will be tangent to the curve. So at each point, the velocity vector is tangent to the curve. It's just going to tell us the same thing it's always told us. Which direction is the function headed? Velocity vector will be tangent to the curve. So we know that this P of t is going to be the parameterization of a circle of radius 3 centered at the origin. I have all the t, so it's going to keep going around and around and around. I'm going to be drawing a tangent, so I'm going to be picking a point, so it's going to be okay. Coffee cup size. So here is a circle. It's going around counterclockwise. Last time I didn't draw another arrow on the other side to balance it out, and it started turning into an ellipse. So I want to make sure I balance it out this time. So at this point, here's at the point 3, 0. So our position P at t equals 0 is going to be 3 cosine of 0 plus 3 sine of 0. Cosine is 1, so 3i plus 0j. So that's our location, 3, 0. We go 3 in the I direction and 0 in the j direction. If we look at the velocity at this point, I just find the derivative of each of these, each of the parameterized equations. So v of t, the derivative of cosine is negative sine, so negative 3 sine of t I, and the derivative of sine is cosine, so plus 3 cosine of t times j. At 0, we'll have negative 3 times a sine of 0 I plus 3 times a cosine of 0 j. So that's going to be 0 plus 3. So our position vector is horizontal. So our velocity vector is vertical. And that's going to be tangent to this the circle at that point. If we add more to this, because up at the top I said position, velocity, acceleration, we know that acceleration is the derivative of velocity. So this is going to tell us how the velocity is changing. So take a minute and speculate what the acceleration vector is going to look like. And now let's calculate what the vector is going to look like. The acceleration vector is going to look like. Now, I didn't explain how to find the acceleration vector, but if you were guessing, are we just going to take the derivative of velocity? Then you are correct, because that's how this stuff works. And we like to be consistent. So our acceleration vector is going to be the derivative of the velocity vector, which will be the second derivative of the position vector. So the derivative of velocity, the derivative of negative 3 sine is negative 3 cosine. The derivative of 3 cosine is negative 3 sine. When we plug in 0, we can see that we're going to be pointing back towards the origin. That's the acceleration as we go around. So the acceleration at t equals 0 is going to be negative 3i plus 0j. So the acceleration in this case is going to be normal to the curve. So the acceleration is what's pulling the point around the circle. The velocity is going straight up. The acceleration is pulling that towards the center. So here's our A acceleration at 0 is negative 3, 0. And so we could see that at every point along this circle, we're just going to get that same picture. Our velocity is going one direction, is going tangent to the curve. Our acceleration will be pulling things normal to the curve. So if I pick a point over here, I've got my position vector. My velocity vector will be tangent to this. Acceleration is going to want to pull this around the circle. So our acceleration is going to be pulling back towards the center. There's our acceleration, our velocity, and our position. ABC, our alien versus predator. I guess that was kind of an inevitable crossover. And what I'm really missing is Tremors versus predator, or Tremors versus aliens, or Tremors versus aliens versus predator. Has everybody seen Tremors? Got Kevin Bacon? Yeah. No. It's definitely not a Ridley Scott. That'd be awesome though. Now that you mentioned that, that'd be kind of cool. No, it's Michael Gross. He's I think the only actor that's been in every single Tremors movie. Does anybody even know who Michael Gross is? I'm just older than you. Family Ties? Wait, it was Family Ties, right? Shit, I don't even know. Anyway, it was Michael Gross in Tremors. All right. So here we get this setup. We've got the position, which is just the location along the curve. And our acceleration is going to be, so our velocity will be tangent to the curve, and our acceleration will be normal to the curve. Our second derivative is going to be, because our acceleration is how we have to change the velocity to keep going along the path. So it makes sense that our velocity will be tangent and our acceleration will be normal. It was Family Ties? All right. Memory is not completely failed. Thank you for that. See, teachers just don't appreciate when students just have computers in the room the whole time. And you can just find stuff out. I just don't understand. She's like, you shouldn't have a computer in class. Why? And then like, you shouldn't have a phone in class. You can have a computer, but not a phone. Like, dude, they're the same thing. This is a computer as well. It's just a small one. You know what I mean? Teachers are weird. They're weird hang-up stuff. You can have water in the class, but you can't have other things. You can have some beverages in class, but you have to put the bottle of tequila away. I mean, so many hang-ups. Yeah, maybe. I think it's the statute of limitations is passed, but I used to, when we had in-person finals back in the before times, when there were in-person finals, I'd always tell my students, if you want to, whatever you want, if you want to listen to music, that's fine. But if someone tells you to turn it down, no question, you have to turn it down because someone can hear it. And stop blowing out your eardrums if everybody else is listening to your music. This also goes for you where your subwoofer is rattling all the bolts loose on your car. Because outside of your car, it doesn't sound cool. I can just hear that you've only got 2 bolts on your license plate. So get over it. Turn the music down. We don't all need to know how cool you are because of the music you listen to. So knock it off. Or your subwoofer will knock stuff off for you. So, because I want you to be chill during the final exam, it's kind of stressful. So if you want to listen to music, that's good. If you want to bring a beverage, and that's the unfortunate way I phrased it, because I didn't want people to just bring water. I said, if you need to bring a beverage, is that your, like a beverage goblin thing, 1 for energy, 1 for hydration, 1 for fun. If that's the way that's the way you are, then that's cool. I want you to have that in the 2.5 hours that I'm asking you to sit in the room to do math problems. And the big mistake was I said, you can bring a beverage. And I had a student who was a little bit of a joker. He comes in and like during the final, he sits in the front row all the time. I was like, you said you could. Yeah. Dude pulls out a bottle of tequila. Tequila Blanco. So I'm like, that's funny. He filled a tequila bottle with water, and that's what he's using to hydrate. And then he goes to open up the tequila bottle. Crack. Mike, nope, that's a fucking bottle of tequila that he brought to the classroom. Then he pulls out a shot glass, pours himself a shot, takes the shot, puts the bottle away, and continues with the test. No, he did not. It was a little bit rude. That's party school rules. You do shots, everybody does shots. It's the rules, man. That's human rules. But anyway, I was just kind of stunned because I was like, that's funny. You're using a tequila bottle for your water bottle. And then I heard that distinctive crack when he opened it. You saved that. You brought a new tequila bottle just so you could verify that you brought tequila to a calculus final. Anyway. Bring a bottle of wine. Yeah. Like swirl it around. Take the nose. But no. I had to let that one go because he just took 1 shot and then put it away. And then I didn't see it for the rest of the day. So that's okay. I had to let that fly. I gotta admit, that was pretty funny. All right, I'm gonna have to revise my rules. Revise my rules. So we got position, we've got velocity, we've got acceleration. So we want to think velocity is tangent to the curve, and I claimed that we saw in that previous example that acceleration is normal to the curve. So we should maybe verify this. So we're going to combine that with parameterizing a function. Thrown off because yesterday we had the power failure right before class started, and they didn't say the campus was closed until like an hour and a half later. I had already left. What am I going to do? But all right, everybody, come back. We're going to have Cal 3, right? So it was like an hour and a half later, and they said, Skyline, they couldn't get the power back on, is what it was. The problem was they sent an update saying, hey, there's a power outage. And I go, we know, that's why we're all standing outside. But they really missed the boat. Because it was a long time before it's like, well, hey, the power's out. We're working on it. You open that text message up with, sorry to keep you in the dark. There's a power outage. Because it's not like anybody's in danger, right? You don't want to make a jokey joke. It's like, well, there's an active shooter on campus, right? Then like, well, let's not make a joke then. But if there's just a power failure and we're all just kind of like standing around waiting, and it's been kind of a while before you said, hey, there's a power outage. We're working on it though. It's like, you go ahead and make the joke. And they didn't. And I was super disappointed. That's pretty much why I left. Anyway, what are we talking about? Oh yeah, distracted. Yeah, I think you just ignore that complaint though. You just be like, oh, sorry. And just like leave it at that. Oh, sorry. And just leave it at that. Because someone's always going to complain. Let's parameterize a function. So spelled X wrong. If you have a function, we want to make sure that this is backwards compatible with what we understand about parameterization. We don't want to have some separate thing where we can't put the two together. We should be able to describe, if we have a function like we have here, we should be able to describe this with parameterization. So if one variable is a function of the other one, just make the independent variable the parameter. So if you have a function, make the independent variable the parameter. If you want to parameterize a function, just make the independent variable the parameter. So if we want to parameterize y equals x squared, just make the independent variable y is x squared, and x is at the parameter. X of t is t, and y of t is t squared. All the points will give you the ones that you want. Spelled one wrong. The relationship between X and Y still holds. And what we've done is just added direction to our parabola. We're still getting the same points X and Y, but now there's some direction to our parabola. Yeah, but I spelled X with the wrong letter. X is the one. It's like a name, right? It's the name of the variable. I spelled it wrong. It's like when people spell my name. When I look at variables, I think of that as the name of the variable. But then again, I also spell numbers wrong. So I'm like, oh, the answer is 32, and then I write 37. Ah, I spelled it wrong. Then we say it's a typo, but I wasn't typing. It was a righto. But that's not appropriate either, because I was wrong. English is stupid. This is why I like math. At least it makes sense, though. At least all the words mean stuff. So we can parameterize the curve, and this does more for us. This gives us a direction on our parabola. Now, if we want the parabola to go the other direction, so the thing that we want to note here is that the parabola has direction. So we can make the parameterization go the other direction. We can change the orientation by changing the direction of our parameter. If we want to change the direction or the orientation of our parabola, instead of going from left to right, we want to make it go from right to left. Just change your inputs. So now when t is equal to 0, x is equal to 0. Oh, that's not going to help. But when t is equal to 1, x will be equal to -1 over here. And when t is equal to, x equals -2 over on this side. So t is going, as t goes from 0 on up, our parabola will be going the other direction. So this will change the orientation of the parabola. So we have a lot of control when we're dealing with parameterization. You'd be thinking about parameterizing a surface and having a bunch of different surfaces. Actually, if you're thinking about a surface like building a sphere, like with the inner like 0, and then like building out a sphere, you're parameterizing the entire solid. We're just drawing a one-dimensional curve. We're looking at points x, y, and z. So if we think about a curve in space, the same thing would apply. So here, I'll put this in space by drawing a z-axis coming straight out here and just making z equals 0 the whole time. I'm just kidding. That's super cheap. I'm going to make z equal to 1, and I'll just lift the paper up. And then, so that's that parabola. That's cheating as well. I can't draw in 3 dimensions. I should just admit that. So if we plug in, if we want to change the orientation of our curve, we just need to change the signs of all the inputs. Notice that I changed the sign of the x, but I also plugged -2 into my y of t, but it got squared. Because even exponents don't respect negatives. It's weird that in Calc 3, I default to IJK for vectors, and in linear algebra, I never write IJK vectors. I just write columns. I mean, it makes sense given the context of the problem, but I mean, make it familiar, dude. But anyway. So our velocity, -1I plus 2t times j. We're not surprised. We're not surprised that our velocity is constant in the x direction because we just parameterized the function. But if we look at this at various points, v of 0 is going to be -1, 0 tangent to the curve. If we look at v of 1, we'll have -1, 2. So we'll go -1, 2. We have a slope of -2, just like we expected. Our delta x over delta y is still a slope of -2, just like we expected. Oops. That was one. Our acceleration is going to be 0I plus 2j. So we can see our acceleration is not going to be normal to the curve in this one. Our acceleration is always pulling up. So 0 plus 2j plus 2j plus 2j. But we can see for this function, we have this nice, well-understood parabola. It is going in the wrong direction. I did change the direction of my parabola. But as for the different values of t, the parabola is always pulling in one direction. That makes sense. That tracks with how we understand parabolas. If we throw things up and the only force is gravity pulling it down, we are going to get the height will be a quadratic function of pi. Any questions? Cool. How's everybody think? All right. So, there are new assignments available on Canvas. Well, they've always been available, but there are new due dates available on Canvas. During the spring break, I want you to make sure that you do take a break. And don't just spend it all just trying to get caught up on assignments. That's gonna do it for today. That's gonna do it for this week. That's gonna do it for the pre-spring break portion of the class. I'll see you all on the following Monday. Everybody have a good spring break, and thanks for playing. Thank you. See you in not quite 2 weeks, but close enough. Yeah, close enough. 11 days.